as a chaotic pool of raw facts, guaranteeing collapse as it grows. To survive, data must form a mathematically rigorous structure. This transformation is called database normalization. It is the theoretical process of decomposing broad, flawed tables into smaller, robust ones. The objective is to ensure that every table describes exactly one entity and nothing else. The primary mechanical tool used to accomplish this is the relational algebra operation known as project. By taking projections, we split a flawed relation into multiple precise tables without losing the underlying data connections. This diagram shows a standard relational schema. Notice the underlined primary and foreign keys linking across these tables. This carefully divided structure is the result of proper normalization. This chart shows the nested progression of the 6 normal forms. They operate as a strict hierarchy. If a table satisfies the rigorous rules of an outer layer, like the 5th normal form, it automatically satisfies all the rules of the inner normal forms. Ultimately, normalization is a matter of structural survival. Forcing more than one entity to live inside a single table guarantees that, eventually, the entire system will corrupt itself. The baseline requirement for relational health is first normal form. To achieve it, data must be stored in a 2-dimensional table, and it must contain absolutely no repeating groups. If an employee has multiple children, you might be tempted to add new columns for child 1, child 2, and child 3, but this creates vast swaths of empty space for employees with fewer children, and it breaks query logic. To answer a simple question like, "Does anyone have a child named Lee?" the system must execute complex, failing search paths across every possible column. This table shows the correct structural solution. By using the project operation, the repeating group is isolated into a completely separate entity table, connected back to the employee. First normal form is achieved. However, passing this test is only the starting line. A table in first normal form remains critically flawed if it still attempts to describe multiple entities at once. If a table tracks both customers and orders and requires a composite key of order number and item number, you face an insertion anomaly. You are mathematically blocked from adding a brand new customer to the database until they place an order, because you lack a complete primary key. This same structure creates a deletion anomaly. If a customer cancels the only item on their order and you delete that item row, you unintentionally erase the entire customer record from the database. Finally, there is the modification anomaly. When customer data is repeated across dozens of individual line items, updating an address requires changing every single instance. Miss 1, and the database generates conflicting truths. These 3 anomalies are the primary enemies of data architecture. They prove that multi-entity tables will always eventually block, distort, or destroy critical information. We fix anomalies using functional dependencies. Written as A arrow B, A acts as a determinant. Knowing A locks in exactly one specific value for B. A structural flaw occurs when a non-key attribute relies on only a fraction of a composite primary key. This leads to second normal form. To reach it, the relation must already be in first normal form, and every non-key attribute must be functionally dependent on the entire primary key, not just a part of it. The mechanical step here is straightforward. We evaluate the flawed table, identify each distinct determinant, and project them into their own separate second normal form tables. The attributes determined by them follow along as non-keys. By executing this specific projection, we separate the customer entity from the order entity. The mathematical barrier drops. We can now insert data about an independent item or a new customer before an order ever takes place. Precisely identifying the determinant is the only strictly reliable method to isolate entities and permanently neutralize partial key anomalies. Second normal form removes partial key dependencies, but a table can still harbor a transitive dependency. This means a non-key attribute functionally determines another non-key attribute. For example, an item number determines a distributor, and that distributor determines the warehouse phone number. Third normal form states that a relation must be in second normal form and completely free of these transitive dependencies. The solution is to split the table, separating the items and the distributors into their own distinct relations. For the vast majority of real-world databases, Reaching third normal form resolves all functional design flaws. Strict mathematical rigor, however, requires handling rare edge cases. One such case involves a table containing overlapping candidate keys. Take an employee scheduling scenario where each employee works one station per shift. Here, the keys overlap. You can uniquely identify a row using the combination of employee, date, and shift, or by using date, shift, and station. We apply Boyce-Codd normal form, which dictates every determinant must be a candidate key. Because both combinations effectively determine the rest of the row, they both function as valid candidate keys. The table satisfies Boyce-Codd without breaking dependency constraints. Third normal form and Boyce-Codd act as the ultimate enforcers. They guarantee that non-key attributes are strictly loyal to their candidate keys, stopping transitive data corruption at the source. Beyond functional dependencies, another structural threat arises when you attempt to house multiple independent one-to-many relationships inside a single table. This creates a multi-valued dependency. Mathematically, it means attribute A determines a finite set of B and also determines a finite set of C. Crucially, sets B and C are entirely independent of each other. This diagram illustrates the problem. A single movie entity connects to a group of actors and independently connects to a group of producers. If you store all three in a single table, the database is forced to duplicate the producer's name for every single actor in the movie and duplicate every actor for every producer. Fourth normal form eliminates this. It requires the table to be in Boyce-Codd normal form and contain zero multi-valued dependencies. We enforce this by projecting the structure into two separate composite entity tables, one mapping movies to stars and the other mapping movies to producers. By separating them, fourth normal form prevents the Cartesian product explosion of unnecessary rows when tracking independent, multi-valued sets. The final theoretical boundary addresses tables composed entirely of keys, operating under highly specific business rules. This introduces the join dependency. It occurs when a table can be accurately recreated by joining multiple smaller tables, but only because a superseding business rule guarantees the data will line up. Imagine a retail database where a customer buys a box set. The business rule dictates that if you subscribe to the series, you must take every single movie in that series. You cannot pick and choose. Fifth normal form, also known as projection join normal form, states that the table must be in fourth normal form and all join dependencies must be explicitly implied by the candidate keys. Because the all-or-nothing business rule exists, we can project the data into a series subscription table and a series content table. The rule guarantees that when we join them back together later, the result perfectly matches the original data. Fifth normal form represents the absolute mathematical endpoint for data division. It ensures that no combination of projections can ever generate false phantom rows upon rejoining. This diagram of the nested normal forms illustrates that database design is not an arbitrary set of guidelines. It is a strictly sequential process of logical refinement. Every step is driven by algebraic logic. We isolate exact functional dependencies, eliminate transitive chains, and decouple independent multi-valued groupings. In practical application, projecting your tables into third normal form is the primary objective. Doing so permanently insulates your data against standard insertion, deletion, and modification anomalies. The outer rings, Boyce-Codd, fourth, and fifth normal forms, serve as specialized tools, ready to deploy against complex edge cases involving overlapping keys and multi-layered relationships. By aggressively enforcing these constraints, normalization elevates database design. It stops being a subjective exercise in data entry and becomes an incorruptible mathematical architecture.